with your topic.
Hello, Martin. Thank you for your introduction. As you have mentioned, my name is Mawad Magdisi. I am the field application engineer, and I will be covering today's topic on the resonant circuits. But before, let me introduce myself. So I am the FAE, the field application engineer, and I have joined KEMET since September 2018 to provide the technical support for our customers in France, UK, and Iberia. So here is the outline of my speech. So there is, at the beginning, I will start with a brief introduction of the context of these applications with a comparison of the different resonant converter topologies. And later on, I will present the different passive components that we can provide for these resonant circuits. And we will give a comparison between the different technologies that we can propose through an application example, comparing the drawbacks and benefits of each technology, and finally conclusions and takeaway. So the context of this topic is really related to the increased power density of power converters. So today's power converters are not only designed to meet the input and output requirement, but also to meet the same efficiency or required operating principles with a reduced volume or at a lighter weight, and with a reasonable cost, of course. One of the solutions to meet such requirement can be done by increasing the operating frequency, and this can be achieved today by the new development of the power devices such as the second GaN, which will give this opportunity to operate at higher operating frequency and reduce the overall volume and size of the power converters. These wide gap semiconductors will also offer low gate capacitance and low on resistance, and also have the capability to operate at higher temperatures and higher voltages. However, this efficiency or the improved power density can be achieved as well by the improvement of the power converter topology. And unfortunately today, with the conventional hard switching, the main drawback of these topologies relies on the switching power losses. So all the benefit that we can reach or achieve with the increase of the switching frequency of the power devices can be limited with the switching power losses of the hard switching. So this is mainly due to the overlapping of the voltage and current during the switching phase of the power devices, during the transition from the on to off phase, or the opposite direction from the off to on phase of the switch device. And in this case, at this time of switching, we will have an overlapping of the current and voltage, which will lead to a power losses. Mathematically speaking, it's related to the power or the power of voltage and current, which will give us the power losses. One of the solutions to limit this effect is to use resonant topologies, which will offer the possibility of soft switching. Soft switching is in reality the fact that during the switch phase of the power modules, the voltage across the power device will be very limited and near to zero, which in reality limit this power losses that we will have in the hard switching. Another advantage of the 0 volt switching is that we will reduce drastically the EMI interferences that we can get through the or due to the switching or the hard switching, and will as a consequence or limit the size of the EMC filter and the input or the output. This kind of topologies, of course, it depends on the topology of the resonant circuits. We will have a wide range of input voltage and load range, which will cover the fluctuation of the input voltage and the load, and can be controlled to give a very stable output voltage. Since we have also in the design of resonant converter topologies a transformer inside the construction of these kind of converters, this will offer the galvanic isolation between the input and output, which is a very required in the power application. But let us at the beginning, at first, see how a resonant converter resonant circuit operates. So here in this slide, we are showing a simple schematic of an RC circuit, which is a series resonant circuit, where we have an AC input, an inductance in series with a resistance, and a capacitor. And once subjecting this circuit with a AC voltage, there's a ripple current or AC current that will flow into the circuit. And the current will have this type of equation as follow. So it will be dependent on the input voltage, of course, and also on the overall impedance of the circuit, which is dependent on the resistance, the reactance of the capacitor, and the inductance. And from this equation, we see that the frequency is a very important parameter here to look in, because if we vary the operating frequency, the input current will also vary. So here, what we show in the plot here on the right side of the slide is the input current as function of the operating frequency. And we can see that at a given operating frequency point, we have a very or the optimal or the highest current that can flow into the circuit. And at this operating point, is called the resonant frequency. So what happened in this equation at the resonant frequency is that the inductance reactance is equal to reactance of the capacitance, and that means the difference between them will lead to zero, and the input current or the current flowing into the circuit is a function of the input voltage over the resistance R. That means that from an energy point of view, that means that the energy is transferred from the input to the load through the LC circuit, at this operating point, the equivalent circuit will be represented only by resistance R. Talking about resistance, there's an important parameter to highlight here is the quality factor, because in this type of circuit we talk more about the quality factor, which is the ratio between the overall impedance of the circuit over the resistance R of the circuit. And in this case, it can be written as follows. So that means if we have a high resistance, the higher the resistance is, the lower the Q would be. And inversely, the lower the resistance, the highest the Q. So how this will affect the operating principle of the circuit. So imagine now that we are having a lower resistance than the one that we are showing here, that lead to a higher Q to the circuit. That means that we can reach easier, let's say, the resonant point, the highest operating point of the current. But as a drawback, here we see that the operating frequency will be limited. That means that if we are far from this bandwidth, we will be far away from reaching the highest current capabilities. However, it will be easier to reach this high current in the nearby region of this Q. So how these features can be used to the design of power converters. We showed previously the operating principle of a series resonant circuit, but here, let's say, we will show how this feature can be used for power conversion. So in this circuit, we have the DC input voltage here that it's switched on and off and converted to a square wave with these switches. It can be a full bridge or a half bridge. And here we have the resonant tank, the transformer, and then the rectifier and the C output, which will filter the voltage, the rectified voltage, and then here we have the load. A typical way to achieve this, or to make the link between this and the resonant circuit, is to have an equivalent circuit between of all this part that we are putting here in the square. Several studies have shown that this can be achieved by making an equivalent, or representing this by an equivalent series resistance, which is dissipating the same power as the load RL.
What? Sorry for interrupting you.
Yes.
We have again those noise issues. Is it possible that you switch to telephone audio? There should be the possibility in below left of your computer, when you click on the microphone and the arrow, there's to switch to telephone audio in the bottom left on your presenter mode. If this is possible, there should be the possibility to call via your telephone and use the microphone of your telephone for the presentation. Is this possible? Can you see this?
Yeah, I will check this.
Sorry for interrupting. But,
no. Sorry, I'm not finding where to add the telephone.
So if you, on the bottom left where you can mute yourself, then you click the arrow on the right side. Unfortunately for me, it's German.
Yes.
The third line from below, there's something switched to.
Yes. Okay. So I will call from the phone.
Can you try this and then we check the voice?
Yes, okay.
To the attendees, sorry for this short break. But we hope to solve the issue soon. Just give us 2 minutes until we have dialed in.
Followed by pound. Followed by pound. Otherwise,
Hello, can you hear me now?
Yes, I can hear you. Please continue like this. I think this is okay now.
Okay, perfect. So I'll mute myself. Okay, perfect. So, of course, to make the equivalence between the power converter circuit and a simple RLC circuit, there is a slight equation between the R equivalent and the load resistance here that we are showing in the equation. So the N square is related to the number of turns ratio of the transformer, and RL is the load in this equation. So of course, now that we have this this equivalent circuit, we can design and check what would be the values of the resonant tank LR and CR. So again, how this operates. So here we have the DC input. It will be square. We will get afterwards a square wave due to the switching devices here that we see in the circuit. And the square wave, if this square wave will be fluctuating or switching at the same resonant frequency of this LRC tank, in this case we will reach the resonance, and the current will, and an AC current will flow into the circuit. One important point to worry about, that is mainly from the designer point of view, is the regulation voltage. So what happens if the input voltage or the output load is fluctuating? And of course, here what need to be done is to have a control loop in order to switch these devices at different frequencies to impact the resonant circuit load and then to affect or to impact the output load and to get a very stable voltage output. So how this will happen? In fact, when we are changing the switching frequency of the power modules, whether it is for in a full bridge or half bridge, what will impact is that since the current is changing, the impedance of LR and CR will change. And here we have CR in series with LR and the load. So by varying or changing this impedance here, what will be affected at the end is the impedance of the load, and thus the voltage across it will be changed as well. So here it is a simple principle as the voltage divider. So let us take an example here by plotting the gain, which is representing the V output over V input. And here we have a normalized frequency, so the operating frequency over the resonant frequency of the converter. And we have different Qs. That means we have different loads. So here, for example, if we have a very fixed load, that means we have a fixed Q. Let us take the curve in yellow and consider that the input now is changing. So if the input is changing, this will affect, of course, the gain. So to keep the same gain at the end, we need to change the operating frequency of our converter so that we get the same gain at the end. So we will we will remain at the same curve as yellow here, for example, but we will reduce the operating frequency at the same factor as the input voltage has changed. If now the load is changing, this means that we have different Q values. Let's take the example if we are moving from Q3 to Q1 and the V input is stable. And to keep the same gain, for example, if we are taking the example of 0.5 gain, in this case, to move from Q3 to Q1, we need to change the operating frequency from this frequency to this one. And this is the main drawback, let's say, of these resonant converters, because the ratio between the Q3 and Q1 in this example can be very high, 2 to 3 times or even more. And this is the issue that we see for light load. That means if we have the case of Q, for example, Q4, and if we are need to keep the same gain, 0.5, we need to have a very, very high switching frequency, which is not reasonable. To overcome this issue, the multi-resonant converters have been introduced. But what does it mean really, the multi-resonant converters? Here we are showing the example of LLC converter. So these kind of converters will have several resonant frequencies. This is why they are called multi-resonant converters. And this can be achieved by adding an additional passive component, can be an inductance or a capacitor. So here the most common one is the LLC, and here we are seeing the topology of these converters, where we have added LN in parallel with the transformer. So this LM in reality is part of the transformer, so there is no really an additional part added to the circuit. And also sometimes LR is dimensioned or configured to be taken into account when designing the transformer. And in some cases, it is different. It is considered outside, or it is a separate component from the transformer. It depends on the power levels and the configuration of the final power converter. So how this will help in enhancing the load control or the frequency issue that we have seen previously. So let's first see the equivalent circuit of the LNC topology here. So again, we can make the same assumption that we have made previously for the LC series power converter. So we have the RE, which is representing all this part from the transformer to the load. And we have LM, CR, and LR. So what will happen now is that if the RE is fluctuating, we will get a different gain in the circuit. We will not go in more detail in the equation of the gain, but we will show what would be a result of changing or fluctuating this load resistance. So in the case of a light load, a heavy load, that means RE is lower than the impedance of the magnetizing inductance, this part of the circuit can be neglected. And in this case, we will have a typical LCR series resonant circuit, as the previously showed. And we will get a gain as we had in the previous case, with a resonant frequency as described here. However, when we have a light load, in this case, we have an RE the same range or bigger than the impedance of the magnetizing inductance. And generally, we have LR much lower than LM. In this case, we will have a parallel resonant circuit, and it can be represented by this gain and this resonant frequency equation. So these two resonant frequencies will somehow define the limit of operating frequency and range of the power converter. So ideally, designer will try to work between these two range, between FP and FS. If the load is getting heavier, will be close to FS, and if the load is getting lighter, it will be close to FP. So when we have an intermediate value of the load, we will get a typical curve of this kind. And of course, this is the preferred region because we have a sort of flat region of the gain, and as well we have a higher gain than one, so we'll be increasing the gain in the power converter. So how will this will be used, or what part can we propose to be suited for this kind of circuits? So let's start with the capacitor solution that we can offer. And as the resonant frequency required, or it's really important to get a very precise value of the resonance. This is really dependent on the values of the inductors and the capacitors that we can get, and it is really critical to get very stable values of these two parameters. And here, that means that the capacitance that we will choose must be very stable with the temperature, with the voltage, and during the whole operating lifetime. Otherwise, this will impact the resonant frequency of the power converters and lead to different gains and different performance than the one required. But how to select the right capacitor technology and series based on the different factors that we will get and requirements that are needed. So here we are showing the different, or mostly all the technologies that we have at KEMET. We have film capacitor, ceramics, electrolytic, and tantalum, whether MnO2 or polymer. But what solution to select? In fact, if we ask ourselves the right question, we can lead to the right series. So for example, for this kind of applications, we have AC voltage. That means the electrolytic and tantalum capacitor cannot be selected just because this kind or these two technologies are polarized, so they cannot accept negative polarization and cannot be used for this kind of applications. So the two families that can be selected are the film capacitors and the ceramic capacitors. And we see that from the film capacitors, we have not selected the deadening capacitors because they are mainly designed for the deadening, for DC voltage. And when we apply AC voltage across them, we will lead to a different failure mechanism than the one the capacitor is designed for. Taking the question, and sorry, from the ceramics, we can keep the class 1, class 2, and class 3. However, since the stability is a requirement here, the class 2 and class 3 cannot be selected, mainly because these two classes of capacitors are unstable with the operating temperature and frequency and voltage, which will lead to different performance than the one required. So from the ceramics, we will keep the C0G dielectric. And this, since this application are also requiring high AC current capabilities, from the film capacitors, we cannot select the RFI capacitors, mainly because they have limited current capabilities, and we shall keep the pulse capacitors. And from this series, we have all these capacitor family ranges that can fit for resonant circuits. And also from the ceramic C0J dielectric, we can select these three families. So we have the KC Link, we have the SMD C0J, and we have the XAG series, which is under development. And it is basically the same as the C0J, but can go higher in temperature up to 150 degrees. Let us first compare the different technologies of the film capacitors. So in this slide, we are comparing or showing you the different type of series that we have, and the different ranges of voltage and capacitance that they are covering. And if we look at the internal construction of these different series, the main difference is related to the metallization. And the metallization has a direct impact on the current capabilities and also on the overall size of the component. So for the families R74, R75, and R75H, which is the newest series 125 degrees, it's a single metallized, whereas other families are as the R76 and R76H, which is also new series 125. Differences on the metallization. So the higher the metallization thickness, the higher the current capabilities would be. However, the size will be affected because the thickness of this material will impact the overall size of the component. So each capacitor series has its own features and advantages and drawbacks. So depending on the application, we may select one of these series. But if we are looking, let's say, on a compromise between very good electrical or current capabilities and reduced size, the best solution would be the double metallized film capacitors. So here in this slide, we are showing a general view of the R76H 125 degrees, which is our latest film capacitor series for the pulse, resonant, and resonant circuits. The main feature that we have, in addition to the previous series, which is the R76, is the highest temperature capabilities. So now we can operate at 125 degrees and have the THP performance. So through all the presentation that we have seen today, in the film technology, we have a roadmap to get higher capabilities of performance with temperature, humidity, and under voltage. So this is the slide. In this slide, you can see if the capacitance that you are searching for is provided by this series and in which level of voltage and capacitance values. As well, in this slide, we see the overall view of the R75H series. As well, this series can operate at 125 degrees and also can operate at harsh incremental capability. So at 1000 hours, 85 for lead space higher than 50 millimeters, and 1000 hours, 60 degrees, 93% relative humidity with the lead space of 10 millimeters. So if we look deeper on the comparison between the R70H series, which is a newest series of the R76, the main difference is with temperature and the humidity. So of course here what we are seeing is the different series that we have as the pulse and resonant circuit capacitors, the ambient operating temperature, the maximum one, and the ambient temperature and the self-heating, allowable self-heating capabilities. So from the performance point of view, we see that the R76 has the best performance in self-heating capabilities. And at 100 degrees, that we see that it has the double value of the previous one, which lead to higher current capabilities. That means at the same temperature, operating temperature, we can have higher current capabilities than our previous series. On the right side of the slide, we see the difference of the self-heating between the R76H, which is in the yellow curve, and the R76 standard one, which is in dotted blue. So here we see the difference that it starts at 60 degrees. That means if your operating temperature is below 60 degrees, you won't see any difference from the performance point of view on the current between these two series. However, as the operating temperature increases, we will have a better performance with the R76H. But another point, let me highlight it again, is that even if your operating temperature is below 60 degrees and you have a high requirement in terms of humidity, it's also worth to consider the R76H because it will help you overcome these issues. From the ceramic point of view, we are showing here the capabilities of the K-Link. So the K-Link, it is using a C0J dielectric, which will offer a very stable performance under voltage stresses, and so we have a very limited change with the voltage, with the temperature, and offers a very low ESR, which will lead to high current capabilities. So here what we are showing is the current capabilities of a C0J 220 nanofarad 500 volts. And we see that at higher operating frequency, higher than 1 kilohertz, we start seeing a very high current capabilities of this series, and we are higher than 50 amps per capacitor. So here is the waterfall table of this series, and we have different footprints: 1812, 2220, and 3640. At the beginning, we started with releasing these big footprints, but then we released the 1812 and 2220. And lately, towards the end of last week, we have released the 2000 volts in 3640, which is really aligned with what we see from the power modules, the voltages required for the second gun power modules. Here we see the capacitance value that we can get, and what of course you may notice is that the low capacitance value that we can reach. And for this reason, we have developed internally what we call the KONNEKT, which is a no-lead frame connection between several capacitors in parallel, which is based on the TLPS, which is a technology used to bond component termination together, which is TLPS, transient liquid phase sintering. And this kind of technique is basically using two types of particles inside, copper and lead. So the lead has a lower melting temperature than the copper, and when we get all this together, heat together, the lead will melt on the copper alloy and form a very rigid and robust matrix, and which will allow the connection with several capacitors in parallel. So this kind of connection is a technology that we can apply on different types of ceramic capacitor. It do not depend on the type of the ceramic. It can be X7R or C0Ga. Different footprint as well. But today we have developed some standard values to help the user to select the right component for his application, and also to reduce the lead time of the production. Another benefit of the KONNEKT technology is that since we don't have a lead that is connected to the circuit, we can orient in a different way the assembly to the circuit. So we can have the standard connection, which is stacking different capacitors in a horizontal way. And we have what we call the low loss. And in this case, we are connecting vertically the different capacitors together. And why is it called low loss? It is really related to the ESR of the capacitor, since the connection inside the capacitor are directly connected to the circuit. There is no need to go to the first capacitor, then to the next, and then to the next, which will induce additional losses in the circuit and increase ESR. So we have the capabilities of proposing these two types of connections. The production will be the same. The only change is in the part number. So we will have only one digit in the part number that will change, and we will receive directly the component or the assembly oriented in the way that you need in the PCB. What is the benefit? Another benefit of this KONNEKT assembly is that we can reduce drastically the overall size on the PCB. So here we are comparing on the left and the right. It is the same example. It was a typical example that we received from the market, and we had to put several series parallel capacitors in series to reach this requirement using the KC link. And then on the right side, we use the same example, but the difference is that we connected each 4 capacitors together to form one component, and we were able to reduce 75% of the overall space occupied on the PCB. So these are the different orientations that we have and the values that we can reach on the standard component point of view. So we have from 500 to 2000 volts, and we can connect 2 to 4 parts, and can be oriented in the standard orientation or loss orientation. Of course, these are not limited to these ones. We can develop some specific part numbers depending on the requirement of the market and the application. So let us now take a typical example and see what would be the selection of the capacitor to reach this requirement. So we have, for instance, here an example for a resonant capacitor requiring a 60 nanofarad capacitor, and need to be able to fulfill or to reach 40 amps at 200 kilohertz and 440 volt RMS at 240 kilohertz, and the ambient temperature here is 85 degrees. So if we take at the beginning the R76 solution, to meet this requirement, we need to put 60 components in parallel, 60 components of 1 nanofarad, 700 volt AC, and a pitch 15. We have here the case size. And with this connection, 60 components in parallel, we can reach the required voltage and also the required current. Each component can do 0.8 amps RMS at 240 kilohertz. If we now take the same example but use the R76H solution, so we see here that in the same example, to reach the same performance, we need only 28 components to be put in parallel. And here we have selected the 600 volt AC, 2.2 nanofarad in a pitch 10, so it's a smaller component and can have a better current capability. Since at 240 kilohertz, we can get 1.52 amps RMS. So again, here we will be meeting the requirement. So just to show you the benefit of the R76 compared to the R70 at this operating point. Also, if we can consider the case-sealing solution, so here we need only 10 capacitors in parallel to reach the requirement. And here you can see from the curve that we have from our KSM tool that at this operating frequencies we can reach 4.1 amps per capacitors, so a total of 41 amps for this component. We can also check the self-heating at this operating point for the ceramic capacitors, and here again we see that at 4.1 amps per capacitors we will be in the safe zone, let's say, because we have a self-heating of 16 degrees, which is below what we define the safe zone, which is 25 degrees Celsius. If we compare the different solutions that we can propose for the resonant type capacitors, of course the R76, if we compare the component number, it's the highest component number, but it is the cheapest solution. However, since we have a lot of components to put in parallel, we will end with a high-cost capacitor tank solution. If we compare this to the R76H, in this case, we will have almost the half of the component that is proposed with the R76. So even one component is cost is more expensive compared to the R76. At the end, we will get a cheaper solution than the R76 because we will get a less number of components that are used in the circuit. And also, we will reduce the overall dimension and size of the occupied volume on the PCB. If we look at the casing, of course, the number of components is the less and occupying the less surface on the PCB. However, it is the most expensive solution. But in many cases, we see that the ceramic capacitor are the chosen one because the weight and the dimension of the overall solution is very critical for the application. So it depends at the end what are the requirements of the application to select one of these series. So if we move on now to the inductors, resonant inductors for this kind of circuits. So as mentioned before, sometimes for these applications, the design of the inductor as part of the transformers is sometimes considered from the customers, depending on the power level and the topology of the power converter. And sometimes this resonant inductors is developed separately from the transformer here. So to reach this requirement, let me first say that we do not develop transformers at KEMET, but we develop only inductors. So if the resonant inductor is developed outside the transformer, in this case, we can provide solution. And the requirement is the same as the ceramic capacitors or resonant capacitors, sorry. That means we need to have a very stable inductor with time, with low losses to reach high Q values for the resonator. For this solution, or to meet this requirement, we generally propose ferrite materials because they can offer these features. So if you look at our data sheet and at portfolio, you will not find directly your solution, and this is due to the fact that for this kind of application, we generally develop customized solution, and it's also defined as critical component from our customers. So generally, we have a specification, we have all the mechanical and electrical characteristics, and we work basically on this kind of specification to develop the right component. However, we have some parts that we are developing to be standard one, but generally speaking, we are developing a very specific component and customized solution. So for this kind of application, we have our BHT material, which is ferrite-based material, and it offers the required stability and low losses requirement from the application. So here we are plotting the BH1T characteristics with different stresses. So here, for example, we are plotting the mu prim and mu second with frequency, which is the permeability and the losses. So the mu second, you see that at this operating frequency around 100 kilohertz, we have the lowest losses in this material, which make them very suited for this kind of application. We see that the mu prime here is changing a little bit with temperature. And we have a Curie temperature around 225 degrees. Again, the power losses is really important, and what we are putting here is the losses behavior with temperature for a given frequency and a given magnetic flux density. So the 200 millitesla are representing the 11 kilowatt power converters, and the 100 millitesla is representing the 7 kilowatt. And also here we are plotting the losses related to the magnetic flux density for a given frequency and different temperature, and we see that there is no difference between 25 and 100 degrees. So again, since these are a customized solution, we can work on the design. We can make different changes from the specification and let you know what are the changes that need to be made and done to reach the requirement. And also we do simulation, thermal simulation to reach the performance required. So interesting information also to be shared is that our team in Japan are designing and developing our own ferrite material. So this will allow us to reach some benefits from what is existing from the market. So as key takeaways from this presentation is that the resonant circuits are now predominantly present in many power converters. And for the resonant tank circuit, we have big numbers of required capacitors. And with KEMET, we can offer a wide range of components to be fitted here for this application specific. And we can support you to choose the best solution that fits the space and will allow you to select the most competitive solution as well. KEMET has the new ferrite material BH1T, which is very suitable for resonant circuits requiring very good stability and low losses. And KEMET makes its own ferrite material, which we can adapt the material type and shape to reach the required customer application. And with this, I will end up my presentation, and I'm open for questions.
Yeah. Hi, Mawaz. Thank you for your presentation. It was very interesting because we are a bit far from the schedule. We will skip this session Q&A. I was recording all the questions, and I will send it directly to you and try to answer to all the attendees. So for all the attendees that have asked us questions, don't worry, we will answer your questions after the tech day today.